Hello, good afternoon. Let's start our new chapter, chapter 7, to test hypothesis test and confidence interval in multiple regression. So let's see what's different from single regression analysis. So the outline is hypothesis test and confidence interval for one coefficient. We're going to start there. And we're going to move on to joint hypothesis test on multiple coefficient. And then we're going to look at other types of hypotheses involving multiple coefficient and variables of interest, control variable, and how to decide which variable to include in our regression model. So when it's not omitted variable bias, right? And still we want to add some variables, then we can look for these values, okay? So let's move on. Hypothesis testing and confidence interval for single coefficient. So hypothesis test and confidence intervals for a single coefficient in multiple regression follows the same logic and recipe as for the slope coefficient in a single regressor model. So what does it says is if we have the model of yi equals to beta 0 plus beta 1 times x1i plus beta 2 times x2i of configuration, if we got the beta hat value and beta 2 hat value and beta 0 hat value, we can test each coefficient separately under the t statistic. Right, so we use the t statistic that is approximately distributed normal 0 and 1. Thus, hypothesis test on one coefficient. Each coefficient can be tested using the usual t statistics, and confidence intervals are constructed the same way, right? The expected value plus minus 1.96, the standard deviation for 5% confidence, 5% significance level, or 95% confidence interval, right? Times the standard error of beta 1 hat. So if you're looking for beta 2 hat, it will be same, right? So instead of beta 1, we can test for beta 2 by using the t statistic of beta 2 hat negative e of beta 2 over the standard deviation standard error of beta 2 hat, right? And confidence interval of 95% will be similar, right? So beta 2 hat plus minus 1.96 times the standard error of the beta 2 hat will be the confidence interval for beta 2. And we can do for beta 0 also, right? So let's look at our data, the California class size data using single regressor and multiple regressors. So under single regressor of STR, we had the coefficient value for the STR to be negative 2.28. So we interpreted, right, like if STR changes by 1 unit, right? TS will change by negative 2.28 by the amount of coefficient of STR. And we know that the intercept is a constant number that says the height of the graph, right? And number 2, if you look at the two regressors, we see the coefficient is now dropping to 1.1 from 2.28, right? And the new coefficient for the percentage English learner is now added as negative 0.65. So what can we do? First, for the single regressor, we can have we can ask if this beta 1 hat is significantly different from 0, right? So in this assumption, we can have the hypothesis, right? The null hypothesis of beta 1 to be 0, and null hypothesis of beta 1 is not equals to 0, right? In this setting, we use the t statistic that is greater than our critical value to reject the null hypothesis and choose the alternative of this coefficient, right? So we can do for this negative 2.28, right? The t statistic is negative 2.28 to our null hypothesized value of 0 over the standard deviation of 0.52 of its own. Then what we have is the t statistic is approximately is greater than 4 and negative, right? So negative 4 point something something something, right? So the absolute value of our t is greater than the critical value, and if we assume preset, right? If we preset it, the significance level to be 5%, then our critical value is decided to be 1.96 in absolute value, right? So the absolute value for t, if it's greater than 1.96, we reject the null hypothesis and we got the t of greater than 4. So the t is greater than our critical value, so we reject the null hypothesis of the coefficient of STR to be 0, but choose the slope moves downward by 2.28 for every STR movement. Okay, so what about two regressors? We have to make the condition of holding, right? So let's look at it. So if you look here, right, we want to start from STR, right? So what is the coefficient? We call it is the the slope, right? The slope of TS to STR holding PCTEL value, right? So we want to know the change of TS, right, accord from the STR while PCTEL is not changing, right? So we can test if the movement of TS is really different from 0 and equals to 1 from 1 when we're holding the PTCEL the same level, we do the same T test, right? So T of 1.1, right, negative the same null hypothesis value of 0 over its own standard deviation of 0.4. Will give us the t statistic right here is negative 2.54, and since this value is also greater than the critical value of 1.96 under 5% significance of two-tailed test, we reject the coefficient of the STL to be 0 and choose the alternative of the slope is negative 1.1. And we can do the same thing for the percentage of English learner, and we can roughly see, right, since the null hypothesized value without any convention is 0, if we want to see here, is simply this over, right? For the t statistic, we can simply divide the coefficient by the standard deviation. And we're seeing greater than, small than 1.9. So you guys see greater than 20, right? So that should be rejected also, and we choose the negative 0.65 as the coefficient of percentage English learner to represent how much of the test score in point will be decreased when additional percent of the English learner is included to the class. Okay, so we can check the t statistic separately, just the same way as we do in the single regressor or multiple regressors. when we run the regression on the software, right, on the data, we can have a command with the regression of the test score with the dependent variable of STR and percentage of English learners, and we're using the standard robust standard error for the error time. So what do we have as a result? We have TS score as a dependent, right? Independent variable, sorry, independent and dependent. So dependent variable, and we have two independent variables of STR and percentage of English learner with one intercept, right? And the coefficients are given here with T statistics, right? So before we write down this equation, right, we want to check the T statistic individually, right? So we want the what? We want to use the coefficient only when the T is greater than the critical value, right? So when only the coefficient is different from 0, right? So when we see that T is smaller than the critical value, then what should we do? So let's assume instead of 20.94, let's assume we got the T of 0.94. Then what should we do? It says the T statistic is smaller than the critical value, right? So 0.94 is smaller than 1.96, so we fail to reject, right, the null hypothesis of beta, in this case 2, right, 2 to be 0. Then what do we have to do is then we have to adopt, right, beta 2 value to be 0, and our equation is not test score equals to intercept plus beta 1 times STR plus beta 2 times PSTLE, but beta 2 we put 0 inside, right? So the equation will be different if we have the T statistic that is not significantly different from 0, right? So we have to look at that part carefully before we write down any equation with this regression result, right? So by checking, we found out all of the T statistics are over 1.96 in absolute value, right? So we're good to go. So what we have to check is here, what is the dependent variable, what are the independent variables, and what is constant, right? So now we can write down this, right here. Our dependent variable of I equals to beta 0 plus beta 1 times x1i plus beta 2 times x2i. What is beta 1? That is constant. What is beta 0 is constant. What is beta 1? That is the coefficient for x1i. What is x1i? We can name it, but here we're going to use STR as x1i, right? So this is STRi. And what about beta 2? It's the coefficient for x2i, and here we have x2 as percentage of English learner, right? So we can write using all these numbers. It's simple, right? So the D of TSI equals to beta 0.686, right? 686.0322 plus beta 1, right, negative 1.10 times STRI plus beta 2, negative 0.649 times percentage of English learner will be our equation. And you can write down the standard errors underneath like that, right? Okay, so moving on. Test for joint hypothesis. So far we have just dealt with single regressor hypothesis test, right? So we just assume one value to be 0 or not. That was our main concern. But now we want to expand our concern, and what happens if we want to set 2 things or 3 things jointly equals to 0, right? So not only HO of beta 1 to be 0, but we want to expand to have beta 1 and beta 2 are at the same time 0, right? We call that a joint hypothesis test. So let's look in here. So let expenditure, right? So new variable is the expenditure per pupil, and consider the population regression model has changed to what? Now we have 3 regressors, right? Regression, we have 1, 2, 3 regressors to represent test score, right? So the null hypothesis that school resources don't matter and the alternative tests that they do correspond to which one? So what are connected to school resources? We will say the controllable variable of the school perspective are STR. They can manage the student-teacher ratio, and also they can manage the expenditure per pupil, right? Then we can say the school resources don't matter, mean it does not change the test score, right? So what do we say? The slope should be 0, right? For both, right? So we want beta 1 to be 0 and beta 2 to be 0 at the same time, right? So what do we want to test under that is, do we want this, or with school resources don't matter, right? Under beta 0, beta 2 equals to 0, our new test score regression will be beta 0 plus 0, 0, beta 3 times PCT, EI plus UI, right? So we're comparing two models. Is it only depending on the percentage of English learner, or school resources does matter, right? So let's look at it. The null hypothesized value will null hypothesis will be B1, B2 at the same time 0. And the alternative is either one is non-zero or both are 0, right? So if we make it into yes or no type, right? If we say beta 1 equals to 0, here, beta 1 equals to 0, let's make 4 conditions. And we can have the result, beta 1 not equal to 0, but we reject the null hypothesis, right? And we can choose the beta 2 to be 0 under the hypothesis test, or we can have the result that is non-equal to 0, right? So what are these hypotheses is implying? What about HO? When B1 equals to 0 and B2 equals to 0 at the same time, right? So we can say, oh, they are both 0, right? That is our H0. What about H1? It says it's okay whether beta 1 non-zero, beta 2 0, right? Beta 1 non-zero, beta 2 0. That's fine. And beta 1 0, beta 1 0, beta 2 non-zero, right? This is fine. And beta 2, 1 at the same time, non-zero. So now we have what? The H alternative. The H null alternative side is way bigger than the fail to reject area. So what do we see is by design, it's harder to what? Reject the null it's hard to fail to reject the null hypothesis if we increase the conditions, right? So when we have just two cases, right? If it's beta 1 equals to 0 or beta 1 non equals to 0, right? reject or fail to reject. We had something like 50-50, right? Let's say. But if we have 4 slots, right, it's not 50-50. It's greater for rejecting and less for fail to reject, right? So automatically the probability of rejecting will go up, and we're gonna see that in systematic if we do this way, right? By one independent occurrence of 2 things, right? So for the joint hypothesis, we have the null hypothesis that the beta 1, 2 at the same time 0 versus 1, 0, the other non-zero, 1, non-zero, the other 0, 1, no 0, the other no 0. This is all for alternative. That is only when beta 1 and beta 2 are at the same time 0, right? So a joint hypothesis specify a value for 2 or more coefficients, that is, imposes a restriction on 2 or more coefficient. So in general, a joint hypothesis will involve 2 restrictions. So how many restrictions do we have in here? We see one value is restricted and the second value is also restricted, right? So we see 2 restrictions in this case, right? And a common sense idea is to reject if either of the individual is exceeding 1.96 in absolute value. But this one at a time, like we have the box, right? Yes, no question. If we do this, the probability is not the normal distribution that we want. It is skewed to the what? Alternative side, right? So let's look at why can't we just test the coefficient one by one, right? So the reason in simple is because the rejection rate under the null is not 5%, right? So we wanted to keep it to 5%, and that's what it means to have 95% of confidence interval. So we want 95% of the confidence interval in at the end, right? At the end. Not 95% in the middle, right? So what we're doing is, if we do separately, right, for beta 1 and for beta 2, we're having 95% confidence interval for beta 1 head and right, and 95% for beta 2. But to combining those two things cannot have 95% confidence interval. That's the problem, right? So let's see. So we'll calculate the probability of incorrectly rejecting the null using the common sense of 5% of significance level or 95% confidence interval for each, right? To simplify the calculation, suppose that n are in then what? Beta 1 and beta 2 are independently distributed. This isn't true in general, but just in sample, right? So let T1 and T2 be the T statistics of beta 1 and beta 2 head, right? So if we can reject both of the, we can do the hypothesis for both and reject the null hypothesis of 0 separately if the T statistic is greater than the critical value. Right? But what is the probability that is 1 at a time? It's 5%. And if we do it 2 times, the value won't be 95. So let's see. So let's look at it with mathematically. The probability of incorrectly rejecting the null hypothesis using the 1 at a time test. So what we want to check is the significance level. Right? So for our conventional setting, we want 5%. But will it will it produce 5% if we do one at a time, right? So the setting is we want, right, if beta 1 or beta 2, yeah, here, T actually was written here. So the T1 and T2 are independent by assumption, right? So we assume independently distributed two distribution of T1 and T2. Then let's have this reminded, right? So let's recall the probability, right, rule. So the probability of A and B, right, is when A happens and B happens at the same time, right? So the probability of A and B is represented with the probability of A plus probability of B negative probability of A. Oh no, A and B is A and B, right? No, probability of, let's see, A and B, right, can be treated like that. And when they are independent, under independent, we can have probability of A and B equals to probability of A times the probability of B, right? So A times B will give us the joint probability, right? So what we have assumed is we're doing the t-test, right? T-test separately, independently, right? So the probability of confidence interval for T1 will be 95%, and what? Incorrectly rejecting the null hypothesis is 5%. So now let's look at the equation setting, right? Here we have the probability of H ner of T1 greater than 1.96 and or T2 greater than 1.96. What do we see here? That is the HA, right? So under a normal distribution, it should be the probability of over, right? For T1 over 1.96, right? This is 1.96, and the probability that is T1 is greater than that, right? And or one more, right? T2 of 1.96 or greater. That is our what is inside, right? So this and or means this is representing our null hypothesis, and if we subtract that probability out of 100%, right, we're gonna get that left and that left, right? That's what we're doing with one negative the the other side, right? So to get this, we can subtract that, right? And to get that, we can subtract this. But we're looking for these values right now. We set that equals to 5%, but we want to know what happens if it goes to, two things combined, right? Will this rejection area also 5%, right? So we're gonna get that as a whole to here and gonna subtract the other part from 100 to get the what? Critical value that is same as 5 or not, right? So here the other is what? 95% of confidence interval for case 1 and 95% confidence interval of the second coefficient, right? And since we are assuming the independency, right, we can have it multiply to get the probability of two things happening at the same time. So what we got is 1 negative 0.95 for both, right? So power 2, this is power of 2. So we can get 1 negative 0.95 to the power of 2 equals to 90.25. And how big did you want it? We wanted 95. But how much we got? We got smaller value than our desired confidence interval. So what it says is, as we already got the concept from rejecting is more prevail, right? So what? The critical value under independence, right? One at a time rejects in more often, right? Critical value one at a time rejects the null more often and having the critical value greater than 5%. So what do we want? We want to match this down to 5%, right? So we can say the size of the test is the extra rejection rate under the null hypothesis, but the size is not 5%. We saw 9%, 9.275%. So in fact, the size depends on the correlation between T1 and T2. Since we have what? X1i and X2i has correlation that is non-zero. So they should have the correlation calculated when we want to get the joint distribution, right? So we're gonna consider it. So that is the one solution. We use the correlation consideration, and one other thing is to use a different critical value in these procedures to make 5% confidence interval after all, right? So we gonna get what? 1 negative x to the power of 2 equals to 0.05. That's what we wanted, but this is not happening a lot. And the method we're gonna use from now is to use the F statistic to consider the correlation into the calculation. Okay, so let's look at the F statistics. The F statistics tests all part of the joint hypothesis at once. So not like the T statistic doing one at a time, we can test at once the 2, 3, 4 things by F statistic, right? So the formula for the special case of the joint hypothesis of beta 1 equals to 0, beta 2 equals to 0 in the regression with two regressors are given like this. So you don't have to remember, all we have to know before we go is what? We're seeing this and that, right? So what we're seeing, the row head of T1 and T2. So what does that represent? That is the correlation between T1 and T2, right? So we can see F is adjusting, right, with the correlation between T1 and T2. So inside we see a average of two things and the squared value modified for the correlation. And this is rejecting like the T statistic, right? So we have T for normal distribution, we have F for chi-square distribution, and this is for 1/1 test, and this is joint test, right? So the logic for rejecting or fail to rejecting is same. When we have a T greater than critical, we reject. And for F is same. If the F is greater than the critical value, we reject. But T is the normal distribution and F is, or chi is a skewed distribution. So the critical value is different, right? So we reject it under large value, but how large we want, it's in here. Here is the selected large sample critical values of under various restriction numbers, right? So before our case, we want to do beta 1, beta 2 equals to 0 kind of restrictions, right? So how many q's do we have? Q equals to 0. So under the q equals to 0, we want the F statistic greater than 3, right? So how large? Greater than 3. And it changes if we have more to jointly test. And this is smaller, the grade is 4 when we have single restriction to test. So it means there is no, what? This is no joint test for the Q1. Okay. So if you look at the F statistic more in detail, right? The F statistic is large when T1 and T2 is large, right? Because we are dealing with the squared value, right? Whenever T1 and T2 is large and or large, right? We'll have the F greater. So more likely to reject the null hypothesis that two things, beta 1 and 2, are jointly 0, right? And number 2, the F statistic corrects the correlation between T1 and T2. Yeah, we can see the correction is happening. And the formula for more than 2 betas is nasty unless you see the matrix algebra, so we're not gonna show you, right? So this is by far all you need for the F statistic, and this give you the F statistics are large sample approximation distribution, which is, I told you already, a chi-square distribution, right? Just like T becoming normal, our F becoming chi-square with what? Large sample with large sample. So large sample distribution of the F statistic follows the chi-square distribution, but let's look this first. Consider a special case that T1 and T2 are actually independent. There is 0 correlation, right? Correlation equals to 0. Then what happens is we can see many rows here, right? That becomes 0, that becomes 0. So the F statistic is only left with the half the size of the two things in squared value, right? So we can say the large sample distribution of the F statistic is what? That is the distribution of the average, right? Average 1/2. Right? Average of two independently distributed squared, right? Standard normal random variables. So we can look at it word by word, right? Standard normal random variables, T1 and T2. And squared, right? So one T1 squared, T2 squared. And it says the distribution of the average of 2, right? So average of 2. Oh, we got it, right? So the F is about average of two independently distributed square standard normal random variables under when T1 and T2 are independent only, right? So if you look at the chi-square distribution with large number of observation, large sample, right? The chi-square distribution with q degrees of freedom is defined to be the distribution of the sum of q independent square standards normal random variables. So what do we see? This is about if we have q equals to 2, it will have what? T1, right? Sum of the independent square standards normal random variables. So T1 square, T2 square plus. That is the chi-square chi-square with Q restriction distribution. And what do we have as a F? F is the average of T1 plus T2 squared value. So how much do we see difference? About what? 1 over Q, right? Here we have Q equals to 2. So what we see is F is 1 over Q times the chi-square distribution of the Q restrictions, right? So that's why we have in large samples, right? F is distributed as chi-squared divided by the number of restrictions, and we saw this earlier, but with different Q's, right, we'll have different critical values, right? And here, number one said, no, not number one, one says, oh, why? So what is it asking for? Why, right? This is Q equals to 1, right? It says if beta 1 equals to 0. And under T statistic, we can have it, what? The critical value, only 1.96. But here, we're testing the same thing, Q of 1. But with with F statistic, we have 3.84. So what is it say? Suggesting it's what? Very hard to reject, right? So what do we say? It is about the joint distribution, joint test for F statistic, but we have only one thing, right? So me, myself, different or not, right? So we have very low probability, right? And that's why in the distribution of F or chi-squares to the number of Q, we're gonna see it in the very rare, right? 3.84. Okay, and since we have the chi-square is literally squared value, right? So we have the critical value higher than T statistic or under normal distribution. Okay, so let's compute the p-values using the T statistic. So we can use the same rule to get the p-value. We're looking at the F table, or we can look at the chi-squared divided by Q table, right, to get the p-value, right? So once we got the F statistic, right, under the curve, well, if we get the F statistic, we can know exactly how much of area is over the value of F statistic, and we call that our p value, right? So we can get the p value, but in this case, since this is what? Squared, right? So it's the starting point is 0 and is strictly greater than 0, so we don't need to do what? Two tail test. We don't do it. We only have one tail, okay? And we can use test command under Stata and use different command under RStudio. So once we finish chapter 7, we're gonna briefly going to RStudio to finish chapter 7 part of the software. So let's look at the example test. The joint hypothesis that the population coefficient on STR and expenditure per pupil are both zeros. So school resources, right, does not don't matter, right? Then we want to set the null hypothesis of beta 1 equals to beta 2 equals to 0, right? So we have to do the F statistic. So what do is we use the test command and use each variable, right? Test STR and expenditure per pupil are at the same time equals to 0. That's our question. The command is very simple, and it will spit out the result. 1, we want to test STR, 0. 2, we want to test expenditure, 0. We want to test both, 0, right? So the result is we got the F statistic for two things right? Two restrictions with this is n negative k negative 1, right? So we get for 20 negative 3 regressors in the model, right? We have 1, 2, 3 regressors, negative the constant. So we got for 16 for the second part of the F statistic, right? So we got the F, which is 5.43, and the probability of F greater is what, 0.047. So what does that mean? It means, right, we're testing two restrictions, right? Under two restriction chi-square 2, we have the 5% significance level critical value to be 3, right? So if the F is in F, not the absolute value, we don't have to do it, right? F is greater than 3, we reject, right? And we got 5 is greater than 3, so we reject that what? This and this are at the same time 0. We reject it. And what is the probability of rejecting incorrectly, right? What is the tail value over our F statistic? It's only 0.0047, right? The probability of incorrectly rejecting that both are non-zero is very rare, right? Then after checking all of this, we can write down the equation. But here we face that problem we had, right? So what I said earlier, to write down equation, we have to check the t statistic first, right? So what do we want? We want each and every t statistic to be greater than our critical value of 1.96 under a single test, right? And let's see one by one. Oh, constants. T-stat is good, right? The percentage English learner is good enough. Expenditure per pupil is good, but we have the one. T for our main concern, STR, right, is smaller than 1.96 in absolute value. So what do we say? We fail to reject that what, beta 1 times STR in setting beta 1 is equal to 0. So we have to write down the equation as follows. Since we failed to reject this one, we're gonna treat that as 0, right? So following the t statistic and everything, we have to write down the TSI hat, right, equals to beta 0 plus beta 1 STR I plus beta 2 times expenditure plus beta 3 times English per pupil, converting to 649.5779 plus which one? 0, right? We failed to reject. So plus 0 times STR plus percentage English learner is negative 0.656 times expenditure. No, in English. Okay, so plus 0.03864 expenditure, negative 0.656 times English, right? So our equation should look like this. But what is missing? We really wanted to know about what the relationship between this one and that one. And by adding this new regressor into the model, our significance of the beta 1 disappeared and it just became 0, no impact. So what should we do? We should keep the variable of interest first in hand, right? So what is the variable interest? STR. So we're gonna keep it no matter what, okay? So it's better to delete expenditure per pupil. And this might be the reason of the imperfect collinearity. Right? So when STR correlation between STR and expenditure per pupil is one, right? Very high. Then we can have what? One thing movement is affecting the other very much, right? So the values of beta will be biased, right? So we don't want to have imperfect multicollinearity and drop one of the regressor. And in this case, we want to drop this one to keep the variable of interest. Okay, so there is a simple formula for the F statistic that holds only under homoscedasticity, but which nevertheless might help you to understand what the F statistic is doing. And for homoscedasticity only F statistic, we have a simple formula for computing the homoscedasticity only F statistic, and we run two regressions, one under the null hypothesis of restricted regressions and one under the alternative of unrestricted regression. So what does it mean to have restricted? We have Q, right? Q non-zero, that is restricted, right? So recall when I had that school resources don't matter, right? That we said beta 1 equals beta 2 equals to 0. So the equation was becoming simpler by dropping these values, right? TSI had equals to beta 0 plus beta 3 times English, right? Percentage of English learners only, right? So this version will be what? Under restriction, restricted version versus unrestricted version of the full thing. TSI hat equals to beta 0 plus beta 1 times STRI plus beta 2 times the percentage, expenditure per pupil plus beta 3 times the percentage of English learner, right? I'm gonna rewrite it. It's very blurry. That will be TSI head equals to beta 0, beta 1, STRI plus beta 2 expenditure plus beta 3 times percentage of English learner. All right, so we want to compare this model to that model. So the compare we fit the R squares of the regressions. If the unrestricted one, if this one, right, is showing better, we reject the null hypothesis of restricted one. So the modeling and the calculation part will be dealt in Tuesday, and let's call it a day, right? Have a good weekend and see you next week.